All right, thanks everyone for coming. So we're having two talks today. One first by Jonathan on APL, the second by Josh on React at scale. And so we'll probably pop down to the bar afterwards to have a drink and get to meet everyone, a couple of new members. And yeah, welcome and thanks very much.
So I'm going to be talking about APL. I'm not expecting you to learn APL at the end of this, so don't be too scared just from the title. I'll get started. So I hate title slides that say a lot about a person, but this is my history if you do want to read it. The important bits for me though are the first programming language I was really exposed to was at university with MATLAB. Over in MATLAB, the mathematics building, doing some matrix transformations and things like that in maths. A little bit of Mathematica in physics, but then my PhD did in Fortran. Along with that, doing a lot of work on computer means you learn Bash, and eventually once I moved out of academia and into some real world stuff, learned R. The important thing for me was that these top three languages are all array languages. I didn't realize that until very, very recently, but that will become important in this talk. So yeah, I've got a PhD in theoretical physics, moved into various fields, so fisheries, cancer immunology, autoimmune diseases, and my personal note is that we've got polyglots. I've learned a lot of languages. So last year I did the Exorcism 12 and 23 challenge, which was try to do 5 non-trivial problems in 12 languages. I'm not doing it in, I think it's 18 there. Plus I picked up some dialogue APL and a language called ROC, which is an ML family, similar to Haskell and OCaml. And then on top of that, this year I'm doing the next Exorcism challenge, which I've learned at least 3 in the last 3 weeks. So I do like languages, I like learning them. I've also got a little bit of each of these, currently trying to learn Japanese. So this talk is not a proposal for you to learn APL and be good at APL at the end of it. I'm not going to be teaching all of the syntax or all of the glyphs or anything like that. The idea here is to understand what APL brings and why that makes it an interesting language to learn and what you can learn from it. So the history of it is in the 50s, Ken Iverson developed a mathematical notation, basically for working on pen and paper, of if you do this transformation to this data with these symbols, you could use this as a tool of thought. There's some precedents for that. So this came about as a different notation for working on lambda calculus, and eventually got implemented as a language. This had the sort of same idea that there was a mathematical notation that worked out. Ken then ended up working at IBM. And then wrote a book called A Programming Language. And at IBM, they decided, hey, this would be pretty cool to put into a computer. What should we call it? Well, there's a book called A Programming Language, we just used that. So APL was born in about the 60s. And in 1979, Iverson got a Turing Award and wrote a paper to give his talk for that was notation as a tool of thought, where he walked through these ideas of what APL brings to you if you do learn that. So in that intervening time, it's sort of come and gone and been considered a stale language or a dead language, but there's still a lot that you can do as a tool of thought. Dijkstra said that APL is a mistake carried through to perfection. I don't think he meant it nicely, but I think there's a lot of truth in that this was a beautiful idea that was implemented really, really nicely. He took it as a bad thing, I think it's great. So I want to go through the notation. You can tell me what the math symbol is for binary addition, for adding two things, putting a symbol between those two things and adding them. A plus sign, great. What's the math symbol for binary multiplication? Star. Okay. Maybe from primary school, you'd use like an X. What's the binary symbol for the maximum between two things?
This.
Sometimes? No, not really. Right, so why did we stop inventing symbols to have mathematical operators for things? Before Iverson wrote down this notation, there wasn't one. There wasn't one widely used. So he came up with this one, which you might have seen as ceiling, but basically a straight line with a little cap on the top that said the maximum of these things. But why do we stop there? Why can't we just have more symbols that represent things we want to do to data? So a reverse could look like this, where there's a symmetry between the left and the right. You might flip something, to take something, to grab the first few elements of it, to transpose a matrix, where you can imagine it's flipped along the diagonal. And then you can do weird things. So you can have things like generate a sequence from 1 to some number. Why can't that have a symbol? Or take the length of something. if you're writing down mathematical operations on data, these are useful things that you don't always have a vocabulary to do, and you can make it as complicated as you like. You could do the solution of ax equals b, just give it a symbol, but solving that is a symbol. So these are the glyphs that are in dialog APL. You might recognize a lot of them from mathematics. We do have some of them. Some of them came out because Iverson had this notation. So we've got the maximum, we've got the minimum, you've got your graders, they're already there. But there's something that each of these does to some amount of data. They're also overloaded. So this iota, you can put an argument to the right, give it an argument to this function, it'll do a sequence from 1 to that value. But if you add a second argument to the left of it, it'll actually be the index of this is that. So there's two meanings to some of these, and this is not the M word. It looks like the M word, but it's not the M word. These are monadic and dyadic, when you've got one argument or two arguments. Same symbol, but two different sort of meanings. And the way that this works is if you have some function, you define it in braces. Because you've only got this option of left argument or right argument, they're always called alpha for the first one and omega for the last one. And you can think of them as the alpha is the thing on the left of the function and omega is the thing on the right of the function. So why did we stop there? There's still more things you could do. You could have things that are operators. So this, when it's a function, is a filter. So you take this filtering out, say with a binary yes, no, filter out these things, but it's also an operator, which means we can give it an extra function and perform a reduction. And for some reason, all the programmers decided that each of these needs its own name, but they're all just take this reduction and apply a function to it. So what we mean by that is if we want to do a plus reduction on this list of numbers, we just take plus and put it between each of the values, and that sums it up. An important point here is that APL is actually right to left, so Haskell you would be using fold R. That's important if you're doing a like minus reduction. You're actually going to take from the right. So when people say reduce, usually you ask people what does reduce mean, you say, well, it's taking a vector of things and making a scalar. But there's no reason to limit yourself to those dimensions. You could have an array. A reduction on an array reduces it. So you can imagine you could do a sum, a prod, or a max over a vector, but you can do the same thing and it'll take the leading axis of an array and just reduce that. So it's essentially what other languages would call a row sum, or a row prod, or a row max. And then APL has another symbol you can use to do it the other way, to take the column-wise sum, product, or max. So this takes an array, reduces the dimension by 1, gives you a vector. So does anyone use APL? This is the IBM 1500 from way back when. If you zoom in on the switches, it had two options. You could either use BASIC or you could use APL. So way back when portable computers started being a thing, this was your choice. You could either use BASIC or you could use APL. I think there was some meeting that Bill Gates went to figure out what to put on the personal computer, and it ended up being not APL, but that came down to one meeting that could have gone very, very differently. So I've got a short snippet of a video here. I won't play the entire thing, but just showing APL back in 1975. So a couple of things that people might have glossed past in there was that the addition of two vectors is something that's actually a little bit difficult to do in a lot of programming languages that we have today. So if you have an X and a Y like that, and you want to just add them together, that's where the array programming part of APL really comes in. But if you try to do that in C, that's just not a thing. You can't just add two vectors. So how do you input these things? This is an old IBM, not quite that old, but slightly less old, IBM keyboard. If you zoom in on that, you can see that each of the keys has a little symbol on it. This is my laptop. There's got the stickers on there that you can get. But each of the usual keys has an extra thing. There'd be a toggle switch you can use to type that in. Or when you're in APL mode, that's the thing that you'd be able to type. So the symbols are all there. They're just on the usual keys you have. Once you're familiar with the language, it's just a matter of remembering where they are and you type like you would type any programming language. But the benefit is you have way fewer characters that you need to type. So it's pretty easy to just type that as a flow. So half in English, half in English. So people complain that APL is just not readable. I'd ask you, who can read the top line for me? Well, one person can. But if I start to tell you what each of these symbols are, so who, the, good, ba, me, good, you start to get the idea that, okay, I could maybe read this if I understood what some of these letters are. Not for every word, but you can get the idea. Can anyone read the second line for me?
Programmatismus.
I was hoping at least one person read it. But again, P, R, O, G, R, A. If you know what the letters mean, yeah, this isn't readable anymore. You're not familiar with it. How about the last one? It's English. Okay. It's old English, right? So we know English, but not this English. So when people say APL isn't readable, I said, well, that just means you don't know how to read it.
What does it mean that each one?
So there is no equivalent of programming is fun, so writing is. So what about this one? Can anyone tell me what this does? It's code. Like, we know how to read code, don't we?
It's that same thing.
No, it's a slightly obfuscated hello world in Perl. But again, if you don't know what these different symbols do, then you don't understand how to read this. So I don't really like people when they say like APL is not readable. Well, you just don't know how to read it. It's not a language you can read. So one of the main points I want to take away is that APL is an array language. So I said before that you can do these things not just with individual values, but with whole arrays of data. So what might be familiar for data science people is having this, say, a sheet of I don't know, sales from different stores in different years. And you put that into maybe a spreadsheet, and you have the problem where you have to stack up data and there's lots of repetition. You have to repeat the year in every one of these things. But once you do that, you can say take it to R and summarize it and take averages, put it through as an SQL and do things like that. But this is one big table of your data. Another option is to store it in arrays. So you could have the sales data and just take each of these columns and make a different dimension of that data. And then once you do that, if you can average over certain dimensions, which we said we can do, this becomes a lot easier. So working with arrays rather than just with one big table of repeated data can be really useful. So what does APL code look like? We saw a tiny little bit of it. I've been belligerent and chosen a very, very long language to compare this. But let's say we wanted to add 7 to every value of an array or a vector. There's a great YouTube talk here from Strangeloop where someone goes through a tour of different languages and shows how hard this is to do in different languages, mainly because of all of this boilerplate. So this is a full C file. We've got some boilerplate up here that we've got to do. We've got to do certain vector operations. We've got to specify types. We've got to do a for loop for some reason, and then we've got language specific things that we need to add to something we're accumulating, and then we have to have a main. In APL, we take the vector and we add 7. So that notation of what do I want to do and writing it out, I want to +7 to everything in this vector. Makes, yeah, APL much shorter. And I'll point out this isn't quite the same as, say, deriving a function that is something that adds 7. This is more expanding out the vector, the value 7 to be the same size and you're adding to it, and then, I guess, looping over it. So some maybe newer languages, so if we want to take the average of that vector, we've got it in JavaScript, we've got to think about, okay, I need a for loop, I need to figure out how long the length is, and I've got to do all of this, and I've got to do these bits. In Python, we have a sum, that's great, but we still have, there's boilerplate here. If we want to take the average in APL, what are we trying to do? We're trying to sum the values divided by the number of values. So we can write out sum divided by the number. So this is average in APL. It's literally sum divided by the length. This is where we do get into a little bit of combinator theory, but this is a fork. So this is 3 functions. You'll notice I don't mention an argument here or anywhere to put an argument. This is called tacit style, where it's implied that there's an argument at the end here. So this 3 functions actually pass as do this, and then between the 2, do this. So if you type those 4 characters into APL, it shows you a nice little AST of what's going on, that this is the reduction, that's the derived function, but the other 2 make it nice. So I can walk through what that looks like. If we define x specified by this vector, we take the length of x, and it's 5 values, put parentheses around it just to show you that that's going to be one function we're going to apply. It doesn't change anything. We can do the sum of those values and get 20. If we apply this 3 functions together, we get 4. That's the average value of that. One of the important points, though, is that this function, average, it would take more letters to spell out the word average than the actual function. So one of the things that I think really helps from APL is this idea of having these primitives that do certain things and not obfuscating that by wrapping it into a function called average. That now you have to look at the documentation and say, well, what average am I doing? Are there special cases? Are there different conditions? What does it take? This tells you everything you need to know about what that function is going to do. Because those are primitives, they only do the things that they do. So that sort of has led people to start reinventing the current languages we have, and we now have a lot more of these ideas from APL making their way back into newer languages. So JavaScript, we can do a reduction, and Python, we can do a reduction with a lambda. This is arguably worse than we had before, but it's there. But it's trying to communicate this idea of you're doing a reduction and dividing by a length. NumPy itself is actually heavily inspired by APL, so much newer, but APL is definitely one of the known influences of that. So what can you do with APL? So this is an example with BizBuzz. So to walk through it quickly, we take the argument to the right, I should say from over here, generate the numbers 1 to 20. This symbol is each, so it's essentially a map. So from them, starts over here, we're going to take each of those, we're going to see is it divisible by 3 or 5, that generates a Boolean vector of is it divisible by 3 and is it divisible by 5 for each of the numbers. Union with 1, so if it didn't already have a 1, we're going to add a 1 into that vector. Take 3 of them, so if it's only length 2, we'll add a 0. One of the really cool things is that APL has a notion of an identity element for each operation. So it knows the numbers, if I need to add a number in there, 0 is the identity of that. So that'll give us length 3 Boolean vector, and this is then filter. It's going to take either this one, this one, this one, the original number, out of that vector. And we end up with what you'd expect from BizBuzz. Another one would be advent of code. So last year I went through as many as I could and solved the advent of code problems with APL. If you're not familiar with this, don't worry too much. But if you did happen to do this one, there was one that looked like poker, but definitely wasn't poker, where you had to sort a hand of cards in a different order than poker. Then figure out what type of hand it was, whether it was like 4 of a kind or 3 of a kind or a royal flush, and then sort them. And I wrote an R solution. I was not happy with how I wrote it, but it was about 100 lines, solved in less than a second, and I wasn't too unhappy with it. This is the entire solution in APL. So this first line is essentially just reading the data. There's no actual real transformation happening there. The rest of it I won't go through, but this solved in under 10 milliseconds. So not only extremely concise, not only extremely clear over what it's doing once you understand the symbols, but also extremely performant. And a lot of that performance came from the fact that it was working on an array solution. Rather than trying to process each of the results individually and then sort them all, it built up this big matrix and just sorted the entire thing. Another one that I really like that I guess is a little bit famous for APL is the one-line game of life. So if you're familiar with Conway's game of life, this line at the top essentially sets up and solves the entire problem. The rest of them are setting up the instances of that. So we have these little cells here. If I think the rule is if there's 3 cells next to it or 4 cells next to it, it lives, otherwise it dies. So you have these things propagating and changing, and they look like they move through the system. But this is all you need to specify game of life. I have a live demo if we want to show it.
Yeah, that's good. That should be it, man.
So this is an editor for Dialog APL. And what I'm looking at here on the right isn't a graphics engine or anything like that. This is literally the contents of a variable. There's a variable that contains an array that is either a dot or a symbol. So like this is just, it's literally a live editor. I can start typing in there and change the code if I wanted to. What I can do instead is run this code that will update that value every 1/8 of a second. So every 1/8 of a second, that data gets updated, and this is the live view of that data. So it's one big array.
Awesome.
How fast do you want it?
It's about-
Fifty of a second.
Try it, nice.
Settled. Twenty-five sound per second. So extremely performant, very, very concise. So did anyone manage to try the challenge? I know it came from an APL challenge, but it's doable in just about any language. No?
I tried and failed.
Okay. So I also threw it at ChatGPT just to see if I could get it to spit out an answer. This is a Python solution. So it goes through each of the components, component 0, component 1, component 2, compares left and right, and does an early exit if it finds that one is greater or less than the other. And if none of those are true, eventually it returns 0. So I mean, that looks like it works. I think it passes the test cases. But we've got these 0, 1s, and 2s everywhere that it manually iterates over. It's a lot of if-else's to keep track of. It's early returns everywhere. I wouldn't want to rely that this does everything that I want to do. Got to build JavaScript version, so it's essentially the same thing. It's just unpacked. So that's a little bit nicer than iterating over 0, 1, 2. But now they're named, and I can imagine a typo in here. Like, is there a typo there? I didn't look, but I wouldn't be surprised if you made a typo there. But the same general idea. So the structuring is nice, but basically the same thing. I got it to build a Haskell one, same thing again, but with pattern matching. But it's still, there's a lot of, it's destructured, and then you've got to make sure you don't have any mistakes in here. There's a lot of repetition. But I guess that works. So how do you do this in APL? So that was what, 20, 30 lines for each of those? This is the solution in APL. So the way that this works is if I have a vector on the left and a vector on the right, and I put a minus between them, we do 1 minus 1, 2 minus 0, 3 minus 9, we get this answer. The x that we said was for the dyadic case, multiplication. When you're using it with just one argument, you do the sign of the answer, of the inputs. So in this case, we want the sign of 0, sign of a positive, and sign of the negative. If you have a vector containing zeros, you can take a set subtraction with the thing on the right. So remove the zeros, and you get this. So essentially, we want to find the first non-zero value. We want to know, are they all 0, or is there a +1 or a -1? We want the earliest one in that vector. So to remove that 0, because APL is right to left, we have to use this happy little guy here, which just essentially Haskell's flip, change the argument order, so it can still work right to left. And then this one just takes the first value. So where we've got one that is greater, we get a 1. We've got one that's less, it's a -1, and we're the same. Because this would be an empty set without the 0, first just inserts the 0 element, the identity element. But again, the idea of what we're trying to do, if you were to write down on paper, what am I trying to do if I know that I can work with arrays and I don't have to do this looping through each of the elements? I want the first non-zero element of the sign of the difference. So if I color those, I want the first non-zero element of the sign of the difference. You literally just write out what you're trying to do, and that's really, really nice for just getting your notation as a tool of thought down. So these are some other solutions that other people have come up with. I won't walk through them, but there's some sorting in there, different ways to do it, but all of them, there's no if or for loop here. You're always working on, I've got 2 vectors, I'm going to consider them by comparing the vectors whole. So yes, APL, extremely terse. I went through this and knowing that that is a good solution in APL, can I write the same thing in R? And yeah, I could. So I take the difference, the sign, the set difference with 0, and then take the first thing. And this works almost. The only difference is that if the left and the right are the same, then this is just a 0, and then the set difference of 0 gives you an empty set, so that fails. So you've got to do just a little bit more work and say, well, if they're both equal, it's 0. If they're not equal, then do this.
Is that the order of the inputs as well?
Yes. But getting to a solution here, because I was able to figure it out in APL first, I would never have come up with this solution first. I would have done the big looping thing and figuring out, well, I'll compare the first one, then I'll compare the second one. This, because R is at least vectorized, if not fully array language, lets you do essentially the same thing. Yeah, I think going through APL is a useful tool for that. So it's not all smooth sailing. There's a lot of things that some people won't like. So there aren't types. For people who like their type languages, there just aren't types. There's floats, and there's complex numbers, and there's strings, and that's about it.
No integers.
Are there times that you would need integers?
Number theory.
Possibly. There's no big structures.
Like counting.
So you can use them as numbers.
Yeah.
Like the fact that they are integers strictly, not so much. There's no big structures, so you can't really build up a hash map easily in this language. There are some packages, libraries that let you do that, but not so easily. Functions, because you have either this case where they take 1 argument or 2 arguments, limits the number of arguments you can do. So having, say, a web server that needs 20 different arguments, you're just not going to get that. But this does force you to think about complexity, and do you always need all of the arguments you have to your functions? There's no real packages. There's a couple of different things you can do to bring code in, but it's definitely geared around workspaces. Of you can load somebody else's workspace and it has functions defined, but it's not like a package manager sort of thing. And lastly, it's definitely not pure. So people complain about should you count from 0, could you count from 1? APL will just let you choose. So that iota function that we started with, that does a sequence from 1 up to some number, you can set IO, the index origin, to be whatever you want, and it will count from there, but it will always count from there. So I think APL does change the way you think. If you just get rid of the ceremony, reduce the problem down to the core operations and work with vectorized stuff, helps you hone in on what you're actually trying to solve. And I think for functional programming, that's sort of what we're trying to do, right? We're trying to create a function that does this one thing and doesn't have all of these other side effects that, you don't have to worry about what am I doing over in the system over here while I'm focused on what's going through this function. So I think for functional, it helps. And then I like this quote that a language that doesn't affect the way you think about programming is not worth knowing. Every programming language I've learned has helped me think about all of the other ones I know, and I definitely did not think about the combinatorics of that when I started. But now every time I pick up one of these languages, I compare to all of the other ones. Well, I like this from that one, I don't like from that one, does this in that one. So yeah, I think definitely changes the way you think. So you ask yourself, what are the fundamental operations being performed here? By reducing that down to literally the primitive mathematical operations happening between data, you get a better idea of what you're actually doing to the data rather than building up like 6 functions deep, and at the bottom of that, it's just a plus. What's the shape of the data that I'm working with? Is it something that goes into an array, or do I really need to loop over individual values? Can I do all of this at once? Or can I do it in several dimensions? And then communicating those ideas, the idea that by specifying just the primitives, you say exactly what you're doing to the data rather than wrapping up in functions. So I'll briefly mention that the one I've been talking about today is Dialog APL. Dialog is a proprietary version, it's not open source, but it is well supported. There are others that are around, so BQN is a lot newer. It's based on Dialog APL, but changed a lot of the syntax, broke away from some of the traditions and done some other stuff that's pretty cool. J, I think, doesn't use the glyphs, instead they use like ASCII characters, but it's boiled down to as short as possible. Wewa is one that came out in the last couple of years that is actually a stack-based array language. They come up with a whole new set of glyphs. And you don't work on passing in data, you just have like concatenated programming like Forth, where you say you have a stack of data and you want to put more data onto the stack and then take things off and operate. You do it that way. And then I don't actually know much about Q, but I think used heavily in finance. So APL, this is Wewa code, so completely different set of symbols, but they're still trying to keep some of the idea of this one, I think is a take, this one is a transpose. There's some similarity there between some of the ones that used to do things, but it's not guaranteed. But this adds a whole bunch of new features. This code generates this logo. They also have an online editor, so if you go to this link, that actually goes to this code live in the editor and you can show the output from this. There are also a lot of other array languages, so when I say that this benefit of having arrays really helps you, there's plenty of other options. So I started out pretty much in all of these. I'm working my way into the Ibersonian ones, and then BQN is like the holy grail of all of these things. Maybe I should learn that one.
Sorry, what's the wolf language?
Wolfram.
Makes sense.
So I've got some resources in there. I'll share the link to this talk. But APL Wiki is basically a Wikipedia site that has a ton of information about all the stuff that I've talked about. There's a fantastic free online book, Learn APL, that I've just finished. Really gets you up to speed with all the basics. There is an online editor for APL that lets you just click on the symbols, so you don't have to worry about how do I enter them. There's just a bar at the top, and that's the purple thing I showed you at the start. And you can just play with it like a calculator. I learned a lot of the stuff I started learning about APL from Code Report, which is the person who runs that, is the host of a really good podcast called The Raycast. And I would say thank you. Do you have any questions?
What's the most complex application you've seen written in APL, a similar language?
So way back when everything was written in these things, right? So like entire computing systems were written in that.
Yeah.
I'm not entirely sure, and Dialog, the company that provides this APL, like they're funded to keep doing that by the people who are paying for it. So there are large scale corporations that must still be using it, definitely in finance. So K and Q, some other languages are using that, and like high frequency in finance. I don't know exactly what they're building with it. There's an offshoot of BQN where someone's doing a lot of video games. But they've written a raycaster in BQN and can now build games in that. No, I don't know exactly what it's being used for, but I believe it is still being used.
Sorry. Yeah, I just kind of spoke about one of the previous slides, but what do you think you can learn from array languages that you can't learn from? What is aside from, sorry, like for me, it does seem like it prioritizes that sort of beauty of the means of solving the problem with glyphs, and then also operating nicely. But aside from what do you learn that you get from function?
So I would say the idea of boiling it down to what are you trying to do, functional still, I think, complicates things by writing functions on top of functions on top of functions when it's really hard to see what are you actually doing at the core of that. Having a reduce operator in a functional sense where you pass in a function and do something sort of hides away what you're doing to that by the time it actually sees the data. And that's not something that's always necessary. Sometimes it is helpful, like if your language just doesn't have the opportunity to do that, then that's how you have to do it. But I think there's definitely something there of what are you trying to do at the core of that function that you can expose.
I guess one advantage to it is that like the abstraction of functional programming languages doesn't always, like, it can cost you the ability to use the vector operations, whereas the array programming forces you to think in a way that you can use the CMD and instructions. But ideally, you don't have to think about it, but I guess then even if your compiler can take advantage of it, you might not realize that it's happening even.
So I think this is USARC. Can't remember how to pronounce it, but an APL written for GPUs that takes all of those benefits of I'm working on arrays. Let's just make it work instead of writing CUDA code.
Are these languages compiled optionally?
Some of them are. Could not tell you which.
Is it like
The dialogue is interpreted.
Most of them seem to sort of promote using like a online editor of the website, right? So you got like try APL,
Yep.
Weaver's got their pad,
Yep.
and stuff like that.
They're all locally installed though.
Yeah.
The local version of Weaver just doesn't give you the really nice like web version.
You can get a language server.
We're spoiled by the web pad. It's good.
So the thing I really like about Weaver is that you can just type in ASCII characters and it will format it to glyphs for
Yeah.
you.
So I didn't mention that, but yeah, it lets you write out a word that means the same as the symbol, and then you can press tab and it changes it with the parser and just into the. It's very nice.
Actually, but I don't think be much of a performance increase when it being compiled.
So I think some of these are both interpreted and compiled. I think like you do the interpreted thing when you press enter, it compiles everything, and it's pretty fast.
if you have like vectors that are not really sized, the inner loop is the vector. If you have the vector, so that's what you're saying, right? That basically, yeah, whether the alpha stuff is compiled or not, won't affect very much the speed because the fast bit, like the takes
It's like a
yeah.
So I guess the primitives are compiled, right?
Yeah.
So you're combining them. And whether or not you need something to be compiled of the primitives.
How
it's also damn fast, right?
does it have good ways to handle like ragged arrays or like grouping operations?
So because you don't really have different structures, you have arrays.
Yeah.
And if they're mostly empty, they're just mostly empty.
And so you just have to have like another a mask variable and a value variable.
Can do that. So that filter function, if you pass it an array of ones and zeros, you filter out an array of ones and zeros.
And then you just have to like pass the mask around.
But that's essentially what the game of life is doing. So I wouldn't through it too much, but this idea is we take the input grid as omega. So this rotates by -1, 0, and 1 vertically and horizontally. So you end up with a 9 grid of your tile where it's rotated in each of those directions, north, south, east, west by 1. So to the left is rotated one left, to the right is rotated one right, up rotated those ways. And then there's just some reduction. So you essentially just count how many values are next to this value by just spreading that mask around.
Okay.
And that's how you get it down to this one line.
So
You just make 9 copies of your array and then reduce.
so you kind of go from a rank 2 array to a rank 3 array, where the third dimension is like copies.
No, it's still it's still a 2-dimensional,
With that.
but it knows that there's a separator between those. So you end up with it's an array of arrays, yeah.
Okay.
The 3x3 grid of 2x2 arrays.
Okay, so that's kind of like a rank 4.
If you're interested, this video walks through this solution, which is almost exactly the same, but showing exactly what it's doing and printing out the intermediate steps. That's this one.
More questions? All right,
Thank you very much.
thanks very much.
Share the link to this.
Yeah, I'll put it on the Slack. And if you're not in the Slack, feel free to join. I'm just gonna pause this recording.
There's stop video on the left.
It's weird, it's not showing video.
Uh,